Hi everyone, this is Graham from Group Red 8 in Section 54, and this is going to be our Project 1 presentation. Essentially our starting points here are that we have beta, alpha, and large T are known constants, as well as distance d, but that's less relevant for the actual solving of our problem. Here we have our acceleration function, or our vector value acceleration function, our horizontal component of the acceleration function, which is given by beta, small t, and large t. And then here we have our vertical component of our acceleration function, and that's given by alpha, small t, and large t. These, when integrated, give us our vector value function for velocity. So here we have the horizontal component of our velocity function, given by the same variables as the horizontal component for the acceleration function. And then here, in this parenthesis, we have the vertical component of our velocity function, and that's given by the same components as the vertical component of our acceleration function as well. Once you integrate that again, so the second antiderivative of the acceleration function, we have the position function, and that is given by this horizontal component of position with the same variables as both the acceleration and vector horizontal components. And here we have the vertical component of the position function given by the same variables as the vertical components of our acceleration and velocity function as well. Then for the sense making of the units, we know that the acceleration must be in terms of meters per second squared in standard units. Beta and alpha both have units of unknown, so those are represented by beta and alpha again. The vectors for the direction are both unitless, so those can be basically ignored in this solving. And then here we have units of time over units of time, so seconds over seconds, and those will cancel through division during the horizontal component. So that's this first chunk, and then we're adding, so there's no like cross-pollination of units, so to speak. Here we have seconds cubed over seconds cubed, so those will cancel through division as well. And then we have minus a term of seconds to the fifth over seconds to the fifth, and those will cancel, so those are unitless as well. So essentially we're left with meters per second squared must be equal to a term of beta plus a term of alpha. So both of these must have terms or units of meters per second squared. And then we can check this with another one of our functions. We chose velocity since it's relatively simple, and it also works very clearly as well in position once we go through this solving process. Here we have our units of meters per second, which is our known units of velocity. And then here our recently established units for beta and alpha are both meters per second squared, meters per second squared. This term, which is time squared over a quantity of time, seconds squared over seconds. So the second squared here will cancel with the second squared in the beta, and we'll be left with meters times 1 over seconds, so meters per second. And that's this term here, the first term that we're adding. Then here, for this chunk of it, we have meters per second squared from our beta, again, and then that is multiplied by units of time per second, or rather, units of time in seconds. And that will cancel with the exponent in the denominator of the beta units, giving us another added term of meters per second. So this first section checks out, and that's the horizontal component. And then for this component, we have alpha, which is meters per second squared. And that's being multiplied by everything within this bracket. So when we evaluate these sections of units, we have seconds to the fourth over seconds to the third. The units in the denominator will cancel the exponent in the numerator. So we just have the term of seconds, as shown here. And then we have a subtraction, so these two aren't interacting with each other in terms of units. So we have seconds to the sixth over seconds to the fifth. And this denominator will cancel the units in the exponent, giving us another term of seconds. And then multiplying both of those by meters per second squared, we will cancel the denominator exponent in meters per second squared, giving us another 2 added terms of meters per second. So this checks out because meters per second equals the sum of these meters per second terms, and so the velocity all makes sense for there.
Hi, I'm Jordan, and this is our pectoral graph. This is our initial landing point, and this is our final point for starting at the time negative t to t for the constant time. This is our delta x, or our known distance that we were given, and this is delta y for, in our situation for Cartesian coordinates, x represents going left and right, and y is up and down.
Hi, I'm Chase. Here we have the individual components of all of our motion graphed. So on the top we have acceleration, velocity, and position, all in the y-axis, all the y component of this helicopter's motion. And on the bottom we have the acceleration, velocity, and position in the x direction. These are the x components. So looking at the accelerations in the x and in the y directions, they don't tell us a lot on their own. Really what's important is that sometimes the accelerations are positive and sometimes they're negative. That's what's most important to get out of these acceleration graphs, because what we see in our velocity graphs is that even though at some points the acceleration is positive and at some points the acceleration is negative, in both of these graphs, the velocities are never negative. For our velocity in the y direction here, we can see that it's accelerating at first, it peaks and then it goes down, and at time equals 0, right here, the velocity in the y direction is 0. It's not moving up and down at all. And in the x direction, we see just at the start, it's not moving at all, left or right in the x direction. And at the end, it's not moving at all in the x or y, or in the left or right direction. And because both of these velocity functions are always positive, what that means in terms of our position graphs is that the displacement will always be positive. The helicopter or the rover will always travel some positive distance. So in the x direction, that means we've defined it's going to move to the right. And in the y direction, we've defined that means it's going to move up. So at all times, all the way from that time period, negative big T to T, the helicopter will always be moving up and to the right, which I realize I've done backwards, up and to the right. So yeah, we can see that here. This is our starting point. This is our starting position in the y direction, and this is our final position in the y direction. That change going from here to here over negative t to positive t, this is a positive displacement. Same in the x direction. We start down here, we end up here. That is a positive displacement in the x direction. Just supporting the idea that the helicopter is moving up and to the right throughout its motion.
Here we can see how all these graphs affect our pectoral graph and how the variables of beta and alpha both affect, our graphs and our motion. As beta or alpha is increasing, it will increase the total displacement and velocities respectively for both x and y coordinates. And you can see that even though for the velocity of the y component it hits 0, that's where you can see on the pectoral graph of the plateau where it doesn't go up or down. It just keeps moving to the left and right, which is seen here why this doesn't hit 0. So you couldn't see it before, but this is our pectoral graph again. And you can see that this, as beta and alpha increase, you can see how the total displacement of delta y and delta x, or d, increase over the time from negative t to t. This is a context-rich problem that deals more so with variables rather than numbers, and it helps us model and integrate the acceleration function to velocity and position, which it's a two-dimensional acceleration problem. So we've also seen this type of problem with the Mario Superstar problem in our lecture, where we can integrate the acceleration function to get the velocity function and position functions, which basically helps us understand and demonstrate the motion of physical objects, even in terms of just variables.
All right. Thank you so much for listening, everyone. We hope you're having a wonderful day. This was, once again, Group Red 8 from Section 54. Thank you again for listening. Bye-bye.
Thank you.
Thanks.